In 2021, the Ocean Acidification Research for Sustainability programme was endorsed by the United Nations Ocean Decade. It sets out to provide society with the observational and scientific evidence needed to monitor, mitigate, and adapt to ocean acidification. Join us in broadening ocean acidification research and action around the world by delivering 7 important outcomes by 2030. 1. Quality data. The global science community will be equipped to provide the high-quality ocean acidification data needed. 2. Science to action. Specific data and evidence needed for mitigation and adaptation strategies will be clearly identified and provided. 3. Observing strategies. Long-term ocean observing systems will be co-designed and implemented by scientists, funders, and end-user partnerships. 4. Biological impacts. The impacts on marine organisms and ecosystems will be better understood and used to support the protection of marine life. 5. Future projections. Societally relevant predictions of the impacts of ocean acidification will be freely available. 6. Public awareness. The public will be more ocean acidification literate, understanding its causes and impacts. 7. Policy engagement. Countries and regions will routinely include measures to reduce ocean acidification in their respective national legislation. Time is running out. We need to act now. From individuals to global entities, every effort, regardless of its scale, holds significance. Join us and make a commitment to help deliver these 7 outcomes to tackle ocean acidification. Register your commitment at www.oars-commitments.org.
Hello, everybody, and welcome to Ocean Acidification Week 2023. You are in the Biological Impacts of Ocean Acidification and OARS Outcome 4 session. I'm Katharina Schoh, and I'm an associate. I'm with the Intergovernmental Oceanographic, Intergovernmental Oceanographic Commission of UNESCO. I would like to just point out that this session is being recorded. So, Ocean Acidification Week is presented by GOA-ON, the Global Ocean Acidification Observing Network. GOA-ON is sponsored by 3 entities. First, the NOAA, the United Nations, excuse me, the United States National Oceanic and Atmospheric Administration. Then by IAEA, OA-ICC, the International Atomic Energy Agency's International Coordination Center for Ocean Acidification, and IOC UNESCO, the Intergovernmental Oceanographic Commission of the United Nations Educational, Scientific, and Cultural Aid. GOA-ON was established in 2012 with just a handful of members. Since then, GOA-ON has grown enormously. We now have over 1,000 members from 114 countries. GOA-ON also consists of 9 regional hubs, which span across continents and oceanographic regions, as you can see in this map. We are hearing from most of these, or have been hearing already from most of these, during OA Week. There's another session on the Arctic Hub coming up this afternoon. If you're not a member yet, we recommend that you join by going to goaon.org. OA Week debuted in 2020 and returned in 2021 when events and conferences were postponed due to COVID-19. Following the successful in-person symposium on the ocean and high CO2 world in Lima, Peru in 2022, we are bringing back OA Week for 2023 to maintain the momentum around OA research and to provide a virtual platform for the ocean acidification community to exchange their latest findings. We are more than thrilled to have a wide range of ocean acidification topics and speakers presenting to you from around the world. I would just like to point out that during presentations, all participants are in listen-only mode. You're welcome to type in any questions into the question box that you will find in the panel. And you can also, when you are ready, raise your hand. There's this raise hand button that you can use. We will then call on you and you can ask your question to the presenters directly. And with this, I would like to introduce you to the moderator of the session who's already joined us. Hello, Kirsten. So this is Kirsten Isensee. She is a program specialist at the Intergovernmental Oceanographic Commission of UNESCO and has been there since 2012. Her work focuses on carbon sources and sinks, where she's trying to distinguish the natural and anthropogenic influences on the marine environment in support of the 2030 Agenda, and the contributing to the achievement of the outcomes of the UN Decade for Sustainable Development. She provides technical advice and works with a great many global networks, such as the Global Ocean Acidification Network, GOA-ON. Kirsten, the floor is yours.
Thank you so much, and I'm thrilled to see so many people joining us this morning. And because we have a tough schedule and many great speakers we want to listen to, I will directly start with introducing the first. And there are a few glitches in between, but we will come to that one by one. So I'm very thrilled to be here, joined by my co-chair, actually, of the biological working group of GOA-ON, which is Sam Dupont. He's an associate professor and senior lecturer in marine ecophysiology at the University of Gothenburg and a consultant at the OA-ICC of the IAEA. His main research focuses on the effect of global changes such as ocean acidification and warming, and particularly then, of course, looking at the impact on marine ecosystems. And with that, I'm happy I can speak and turn off my camera.
Thank you, Kirsten, and it's great to be here. So welcome, everybody. What I'm going to try to do today is give you a little bit of background on this session and what is behind this session, and also like extend together with Kirsten a little invitation for you to contribute to these different initiatives. But basically, this session is about biology, and biology is really at the core of what we need to do if we want to address ocean acidification, because we basically can't just focus on one of these other aspects. It's between the chemistry and society, and if we really want to implement some meaningful actions, we really need to resolve the biological impact. And this is, as you probably know, not an easy task. There we have a lot of tools that we can use, from experiment that you can do in the lab, in the field, using natural analogs like the CO2 vents, and also using natural gradient. You can also go back in time using paleo, and all these tools have been used today. But despite like really many years now of biological studies, there are still a lot of questions that needs to be addressed. And many of you have seen, I'm sure, this figure that from Jean-Pierre Gattuso and Ulf Riebesell published a few years ago, saying like basically we need to move from over a simplistic biological experiment to more ecosystem-related, long-term, and including multiple stressor studies. And it's still quite relevant today, I would say. We still have a lot of these questions to answer, but maybe we have to move also toward more action, and that's what I'm going to go to. But when GOA-ON was established, biology was there already. And we realized that there was a need for a really strong reflection about what kind of biological question we need to answer. And that's why within GOA-ON, we created this working group, the biology working group, that is co-chaired by Kirsten and myself. And we had multiple versions of that, but one of the first meetings we had was in Monaco. And that's where we basically highlighted like 3 main tasks for the working group. When we wanted to be able to provide a biological perspective of what the chemical monitoring should be, then also try to identify what kind of requirement of biological monitoring focusing on ocean acidification should be. And finally, we wanted also to develop some kind of theoretical framework that allows to link chemistry to biology. So these are kind of big tasks, and we decided to prioritize. And the first one was the task number 2. So we decided to say, okay, if we decide to start a biological monitoring program to identify the impact of OA, how shall we do that? And we gathered this group of fantastic people here. And we had a beautiful workshop in Sweden in 2020. And we worked really hard on that. And I'm really proud to say that we published the first paper of the biology working group. So if you haven't read it, I strongly recommend to have a look at it. It's really providing you with the tools of what to measure, where to do it, and for what purpose. If you don't have the courage to read the paper, you can always watch the video that has of the seminar, the GOA-ON seminar that we did with Steve a few years ago, and it's still available online. And it's also part of the OA training of the Ocean Teacher Global Academy. So we are also really happy that this paper has been nominated for a prize. So fingers crossed, that would be a nice way to implement what we suggest. So as I said before, like a lot of things have happened over the last 20 years in the field of OA. It's much more visible. It's one of the SDGs. There are more than 10,000 publications, and we have really organized structure like GOA-ON, OARS that has been presented at the beginning of this session. But sometimes it's good to step back and say, did we succeed, or are we moving in the right direction? And in a way, yes and no. Scientifically speaking, we learned a lot, but when it comes to reducing carbon dioxide, we didn't contribute so much, since it keeps going up. And we see more and more the impact of these CO2 emissions. Like this year has been record-breaking in many ways. For temperature, for example, they had like these heat waves that have been unprecedented. And the latest calculation tells you that we basically have 6 years to fix the problem, because after that, we won't be able to stay under the 1.5 degrees. So yes, we as a scientific community contributed a lot in the field, but there is no action. So we need more action, and there are things that we can do. I think this is also a brilliant paper by Jean-Pierre Gattusos, highlighting all the things that can be done, from mitigation on one side and adaptation on the other. But the focus really is that we know a lot. We need to act more efficiently, and that's why OARS was created as a UN-endorsed program for the UN Decade for the Ocean. And this Ocean Acidification Research for Sustainability also have a really strong biological focus, and that's the outcome 4 that is kind of organizing this session here. And we had co-champions, and together with a working group, and you have the composition here, we contributed with a white paper, which is kind of a roadmap of what we want to achieve in the future. And so this paper are available online, so I strongly recommend you to have a look at it. And we identified like some important things that needs to be addressed if we want to move toward more action. So we need to be more inclusive, work across disciplines, but also with different types of community. To do that, we will create dialogue, like workshops to work together, have more an interdisciplinary approach. There's also a lot of information that can be exploited in a different way, and that can be done through working groups to summarize the existing information, or meta-analysis and database that will allow us to create new knowledge from what we already know. And then we also need to provide recommendation for what research is really needed if we want to implement solutions. So not just curiosity-based science, but really focusing on action. And that will be through collaboration with other outcome of OARS, for example, the outcome 2, to talk to the data users, talk to the stakeholder, and try together to find solution and do the science that matters. And then with this focus on solution, also test and try to find the best way to implement things like MCDR or ocean alkalinity enhancement that will be discussed later in this session. So work on best practices. And to do that, to implement that, that's where we started to develop some activities. So for example, the OA-ICC organized training on meta-analysis, so how to use the existing data that are available to the OA-ICC portal, like this biblio database, this database with biological information, to create new information. And also many of us contributed to the guide to the best practice for ocean alkalinity enhancement research. But that's just the starting of implementing this outcome 4. And there are many other ways to contribute to that. And what you can do is join forces with us, come with your knowledge, your time, and you can also register your commitment. And maybe, Kirsten, you want to say a few more words about that?
Yeah, indeed. So this website is now open for OARS commitment, and commitment can start with you as an individual for being able to really dedicate some of your time, of your thinking to OARS and how you can contribute, but also, of course, your institute and organization can put in commitment. It's we hope to really we had 1.5 years of OARS thinking what we want to achieve. I think to really not be only reacting, but also thinking ahead a little bit strategically. And now it's a time to implement these thoughts. And so for that, of course, the whole OA community is required, and we hope of your input. There's also a call out if you're on the GOA-ON email list for working group members. So a big shout out to everybody of you who would like to join us in the OARS4 working group or in any other working group. Just send us a small letter and a tiny CV, and so that we can hopefully work together in the future.
So that's a good conclusion. So a lot of things done, a lot of things to do. We need to move toward action. Biology is complicated, but it's important. So please come and play with us. We need all the help we can get if we want to implement those things. So I'm looking forward to do the rest of the session, and I pass the mic to Kirsten as our master of ceremony.
Thank you very much. And we were supposed to have a nice video from Diane Lavoie from Canada, who wanted to present her work really as well on the Gulf of St. Lawrence. Unfortunately, there was a tiny technical glitch, and we will need to add that afterwards to the YouTube video. So another reason to check out the GOA-ON YouTube channel to also see that great talk. So we will directly move to the next session talk by Murat Belivermiş. I'm sorry for not pronouncing it correctly. He's a biologist who works at the Istanbul University in Turkey. His current research examines how marine organisms are affected by environmental changes such as oceanification, warming, and deoxygenation. And he kind of subjects marine invertebrates to a combination of climate-related stresses and xenobiotics to better understand their capacity for acclimatization and adaptation in the near future. We will have a couple of minutes after each of the following talks for question and answers, so don't be shy. Put them in the chat, put them in the question and answer box, or raise your hand so that we can then also have some interaction afterwards. So the floor is yours, Murat.
Hello, everyone. Do you hear me?
Yes, and looks great.
Okay. And hello, everyone, and many thanks for this great organization. Today, I will present our ongoing some results of our ongoing study about ocean acidification and temperature rising. And the title is Laboratory Studies on the Effects of Ocean Acidification and Warming on Mediterranean Gorgonians, Physiological, Transcriptomic, and Epigenetic Responses. So gorgonians, like other animals, like other marine animals, are under environmental change, and the current rate of climate change and related factors may outweigh marine organisms' ability to adapt future conditions. And Mediterranean gorgonian corals are threatened by several major factors like acidification and marine heat waves. And these drivers are more intense and more frequent in Mediterranean compared to other oceans. And there is a huge body of literature showing marine heat waves and following mass mortality events in marine animals and marine organisms. And the most effective, one of the most affected phylum is Cnidaria, and also corals, of course, and specifically gorgonians such as Paramurcia clavata, Eonicella cavolini, and Eonicella singularis are most affected species from marine heat waves and warming. And this is one of the latest mass mortality events following the heat wave of summer 2022 in French coast. And we see from the picture that the Paramurcia clavata has died because of warming in 2022. And there are some studies reporting the biological effects of warming in gorgonian species, and there are a wide variability of temperature in the studies. But we see that about 25 the gorgonians responds negatively to the temperature, and 25 is a critical temperature. At 25 and above 25, we see some negative effects like necrosis, like reduced nutrient. And if a longer time, we see some coenzyme loss, tissue loss, and died colonies in laboratory studies. So, but below 25, we don't know very well the effects of warming, and we know that most of the warming marine heat waves can't reach 25 or above degrees. So we don't know the biological effect clearly below 25. And about acidification, there are limited studies about the Mediterranean corals, and some of them is about Calodochora spitosa. And there's only one, as I about the gorgonian coral, Corallium rubrum. And of course, there are a lot of study about tropical corals and showing that ocean acidification cause negative effects in the corals, such as calcification decrease. But our knowledge is limited about the acidification on Mediterranean corals. So we focused in the study on transcriptomic and epigenetic change induced by acidification and temperature rising. So phenotypic plasticity is critical for organisms like gorgonians, like slow-growing gorgonians, because adaptation and evolution might not be fast enough to cope with environmental change, rapid environmental change. And DNA methylation, for example, is an epigenetic mechanism, can provide additional time for genetic adaptation. And DNA methylation could offer slow-growing corals a greater ability to buffer the impacts of environmental change, and DNA methylation control or adjust gene expression in the organisms to cope with this type of environmental change. Sorry. So there are some studies showing the significant increase of DNA methylation in sclerectinian corals, but we have no the epigenetic change in the gorgonians in this regard. So the aim of this study is to understand the physiological responses of the gorgonians to warming, just the critical temperature of 25, and acidification and their combination over 2 weeks, and to understand underlying mechanisms such as transcriptomic mechanism, transcript, and epigenetic mechanism on phenotypic plasticity. We collected the samples from Northeast Mediterranean Sea in Aegean Sea, and more specifically from Dardanelles Strait. And these are the species, Nucellus singularis and Paramurcia clavata. These species are actually endemic and very special species for Mediterranean, and they are from class of Octocorallia and the family of Gorgonidae. And this is our experimental setup, and we have a full factorial design of pH and temperature, and we have a totally 12 aquarium for true 3 replication of temperature and acidification. And we have a control aquarium for low pH, high pH and we have a control treatment for high pH and low temperature, and one stress factor as high pH, high temperature, and one stress factor as low pH, low temperature, and a combination of stress factors as a low pH and high temperature. So we acclimated the corals to the aquarium for 1 week, and at a pH total of 8 and a temperature of 20. And the experiment has been done at pH total of 8 and 7.65, and a temperature of 20 against 24. And these are some of experimental conditions. We collected Eumicella singularis at 15, 16 meters. Paramuricea clavata were collected at 35, 36 meters. And fragments from each colony were glued to the silicone support and allocated to the 12 aquariums. And we use artificial seawater at a salinity of 35, and pH and temperature were controlled by aquarium and data logger of IKS Aquastar. And PCO2 was lowered by bubbling of pure carbon dioxide, and the probes were calibrated with well-known TRIS buffer of Andrew Dixon. And we measured polyp activity and oxygen consumption rates as the physiological parameters, and we measured global DNA methylation. For this methylation rate, we calculated percentage of methylated DNA, and we quantified 5-methylcytosine methylation compared to the all nucleotides, because the fifth carbon of the cytosine is the most commonly methylated part of genome. And for transcriptome, we did a de novo transcriptome assembly, and we cleaned the data by using orthologs of Eumicella verrucosa. And as I said, this is an ongoing study, and we have some works to do. And for example, now we are doing an experiment with Eumicella cavallini, the other gorgonian species. And results, and for oxygen consumption, we saw a significant effect of the combination of pH and temperature. And we saw the highest level of oxygen consumption in low pH, high temperature group. And effects of temperature actually increased in low pH we see here. And for polyp activity, after the lab acclimation, we saw an increased polyp activity in warmer condition. The red line and the orange one shows the warming factors, and we saw the increased polyp activity in warming. For transcriptome, we have complicated data, and we used some bioinformatic tools for data processing and orthologs of other species of Eumicella. And we annotated, and at the end, we annotated about 4,000 genes in transcriptome. In this table, we see some results of transcriptome, some first result. And in this table, we see the significantly upregulated and downregulated genes in the genome, and we see that the high temperature alone is the most effective temperature parameter actually, and is far more effective than low pH alone or the combination. And if we zoom in this gene upregulated and downregulated genes, we see that some biological process in molecular function and KEGG pathways, we see some difference with a control group. And as a result of transcriptome, we can summarize that high temperature induced up-down regulation in transcript involving intracellular transport, protein cargo and protein export, protease and isomerase activity changed significantly, especially in endoplasmic reticulum. And DNA methylation in Eonicella singularis didn't change significantly in pH, by pH and temperature and the combination of these factors. And we saw high variability of DNA methylation. And the global DNA methylation percentage is about 1%. And this is actually fall into the other 76 octocoral species reported in the world oceans. And we didn't see any effect of pH and temperature on oxygen consumption rate in Paramuricea clavata. And in the Paramuricea clavata, we see some decreasing of polyp activity in all treatments, but this decrease is very clear in warming conditions in the red and in the orange line. This is a contrasting results to the Eonicella singularis. And conclusion, low pH and high temperature and their combination didn't lead to necrosis or mortality over 2 weeks. Polyp activity and oxygen consumption rate were significantly increased in Eonicella singularis under the combination of low pH and high temperature. DNA was methylated Eonicella singularis, and it could be detected by a classical ELISA method. However, phenotypic plasticity under the low pH and high temperature it didn't associate with DNA methylation in this species. And although our temperature is about 3-4 Celsius degree above the summer maximum of the collection site, we didn't see an acute detrimental effects indeed. And as a last slide, limitations and future needs. We have limited data for the local variability, actually, for pH and temperature. And we need some high resolution, long-term pH and temperature data for the remaining part of the study in the collection site. And 2 weeks exposure have provided as variable data, but we need some long-term experiments, especially for the epigenetic parts. And gene scale DNA methylation profiling and other epigenetic mechanisms and transgenerational studies can be very good states to understand the role of epigenetics in acclimatization in this species. And thanks for listening. That's it.
Thank you so much, Murat, for this very interesting talk. And though we are running a little bit late, but we have an interesting question from Maribel Garcia Ibanez. Very interesting work. How did you choose the value of 7.65 as low pH values? Is it based on future projection? It seems really low pH, a really low pH value for the Med-C, with a expecting increase in total alkalinity related to the increase in evaporation through warming. It may be that those low pH are even not reached by 2100. Thank you.
Yes, as I said, our actually monitoring, pH monitoring is not good in collection site as well as in agency. So actually, we have some data showing that 8.0 is an pH total value for is normal for agency for the collection site. But yes, this depends of the future estimation of carbon dioxide emissions, and it depends of course the coastal acidification, because sometimes we see very effect of acidification because of mucilage or eutrophication. So actually, we think 7.65 as a result of atmospheric carbon dioxide emissions and coastal acidification.
Okay,
But
thank you very much.
Yeah. Okay.
Yeah, thank you very much. I think it's also just a tiny follow-up question. To know the natural variability, and as you said in your last slide, it will be important to have a good monitoring to know the natural variability as well. Then in the next round of laboratory experiments to have a better idea about what the settings of extremes should be.
Yeah, we need some very good data loggers for the monitoring site to see the natural variability of temperature and pH actually.
Yeah, thank you very much. And I think there are probably more questions for you, but so they can reach out to you directly, right? Okay, thank you very much. So we will go to our next speaker, Laura Soto de la Nieves, who's joining us from the Instituto Português do Mar e da Atmosfera. And she's specialized in assessing the impacts of global change on coastal ecosystems using field and laboratory experiments. She worked in the US and Brazil, and now is based, as I said, in Portugal, where she works on the impact that ocean acidification will have on coralline algae as well. She did that for her PhD, and now is working as well on shellfish aquaculture and fisheries. And so I'm looking forward to your talk. And again, there will be a couple of minutes for questions after her talk. So Laura, the floor is yours. Thank you.
Bom dia from Portugal. Thank you for the presentation and thank you for the invitation to be here. As we already know, ocean acidification is already having an impact on the shellfish industry, especially in areas more where there is upwelling or where there is elevated CO2 concentrations. The ocean acidification experiments have found divergent responses. Some of these responses might be related to the stage of development of the organism. We have seen that the larvae and the juveniles are much more sensitive to ocean acidification. Also, the time of exposure, we have seen that long-term experiments have found sometimes parabolic responses. And also the CO2 level tested that has to be realistic and according to the IPCC projections. The local seawater conditions are very important, like salinity or the total alkalinity. And we had to consider all these factors in order to know what will be the effect of ocean acidification on the shellfish industry and ecosystems. So this is an extension of a previous work published in 2021. It was a long-term experiment where we found that after 200 days, there were some growth losses on shellfish juveniles, but there were no mortalities. There were no differences across treatments for the mortality. We know that under ocean acidification, cell damage is expected to increase, especially during fishing operations like dredging. And shellfish is expected to be less resilient and vulnerable to predators due to these changes. What we don't know is what will be the effect of ocean acidification on the self-strength and the high total alkalinity conditions. So the objective of this study was to assess the effect that ocean acidification will have on the self-strength and integrity of Camellia gallina juveniles. So the experiment took place at the IDMA station of Tavira in southern Portugal. In this station, we have successfully bred different commercial shellfish species, some of them novel for aquaculture, such as Camellia gallina, the species that we are going to be talking. And some of the few ocean acidification experiments with shellfish in Portugal were carried out at this station. So the particularity about this station is that the seawater has a high alkalinity of like 3,400 in this range. And when we compare it alkalinity at the station with other locations of the coastal lagoon, such as 43 kilometers away, the station of the University of Algarve, we see that there is a big difference. It's in the range of 2,400. And when we measure the total alkalinity right in front of the station at Tesos Beach, at 200 meters away, is in the same range that in other location of the coastal lagoon. So we know that it's a local event, probably related to the sediments full of cell debris that are below the station. The only previous experiment done with a long-term experiment with this species in Italy, where was carried out in a lower total alkalinity of 2,900, and they found that there was an effect on growth, but also on the survivorship, something that we didn't find. And when we compare our results with previous results carried out at the station that were shorter, they were from 75 to 84 days, the authors always found a neutral or even a positive effect. So the striped Venus clown is a wide distributed species. It's a targeted species for the commercial dredge fishery of several countries like Portugal, Spain, Italy, or Turkey. It's not cultivated. There is no aquaculture for this species. It has a high culinary value and is some of the main ingredients of some emblematic dishes, such as the spaghetti alle vongole in Italy or la paella in Spain. But the overexploitation and recruitment failures make this species an endangered species. So the experiment took place at the station of Tavira. Because the water is pumped from an underground tank, we first equilibrated with the air, and we have three different treatments of the pH levels are based on the EPCC projections. We have 4 replicates per treatment and 200 individuals per replicate. So we did a gradual acclimation of the organisms of 2 weeks. We feed them with 2 types of microalgae. We froze them, part of these organisms, for the south stream measurements. This is the machine that we use for the south stream measurements. The biometry was measured on the right valves, the length, width, and thickness, and also the cell weight and organic content. And the left valves were used to assess the maximum load sustained. Okay, let's see how it cracks. We also see like some SEN images to see if there were differences on the cells, and also calculate the relative concentration of calcium and carbon through EDCs. We found that the length, width, and thickness of the control juveniles were a little bit higher than in the high CO2 treatments, but there were no significant differences, and only the thickness significantly decreased with CO2. The organic content also decreased with CO2, but there were no significant differences, and also the cell weight, but again, with no significant differences. The south strength have a tendency to increase with CO2, but there were no significant differences, and we divided into side groups. So the smaller clams, the force applied has to decrease with CO2, while in the bigger clams, the force applied increase with CO2. We have like different responses depending on the size. So this suggests that maybe there was a change of shape. We did not measure this, but there are new articles that suggesting that these organisms have a plasticity to adapt to ocean acidification, and they could increase their bioconvexity, becoming more like stronger to ocean acidification. And we found the only significant predictor for cell strength was cell thickness. Okay, and it was for the three pH levels, 3 CO2 levels. The SEN analysis showed us that there were 2 main layers, an internal layer and external layer, something that we were expecting, like in most benedids. We found that even though at the central area there were no differences on the calcium and carbon ratio, but at the ventral margin, the youngest part of the cells, there were differences, and under intermediate level it increased, and under high CO2 level there was a significant decrease. The same images show us that under intermediate level the growth lines were more accentuated, and under high CO2 levels they were more irregular and less accentuated. While at the external layer of the cells, it seems that there were more alignment of the crystals under control conditions, while in the internal layer we couldn't see like any differences. So the conclusion from this experiment was that ocean acidification will not affect the self-strength of Camellia gallina when cultivated under high total alkalinity conditions, but in the long term, the growth and the self-integrity of these organisms could be compromised. Also, the best predictor for self-strength in compression experiments was cell thickness, something that agree with the previous experiments done on this topic. We need more studies where self-strength, shape, and other variables are measured simultaneously to confirm the plasticity of the organism. And there are solutions that maybe the alkalization of seawater could increase the self-resilience under ocean acidification, and also an adaptation of the fishing gears. This is the experiment that we already published, and the experiment that I already saw you is under review in Marine Environmental Research. And I don't know if you have any questions.
Thank you very much, Laura. This was great. And we already have one question in the chat from Yuri, who asked if I understood correctly, you said the treatment have been set using IPCC projections for RCP 8.5. Are those pH levels directly from the IPCC models, coarse resolution of oceanic models, or from downscale projections at more regional local scales, as the local dynamics of the lagoons might really affect the trend of pH? But he's also aware that there might be not a downscaled model, because that is probably something which is starting, I think, a little bit everywhere. But
okay, here the water is has a very high alkalinity, seawater. Most of the experiments done, previous experiments done at the station, were carried out at much lower pH levels, because it was difficult to. You had to inject a lot of CO2 to be able to lower the pH. So we follow the IPCC models. We try to keep realistic levels, not to find an effect, but to keep realistic levels, to make a gradual acclimation of 2 weeks, and also to keep it as far as possible. That's why it's the longest experiment done with this species so far.
okay. Thank you very much. We also have another question from Luia T, who has actually 3 questions. How did you execute the pH acclimation in 2 weeks? For example, how much unit of pH did you decrease per day?
Yeah, but it was not, yeah, okay, I'm sorry. Did you see, okay, we have this pH controller, even though that it's better to have fluctuating pH levels, because that's more realistic, right? The pH controller, it doesn't, say it has a range of 1. So we actually don't have always like a linear pH. We kind of follow also the natural variability, because the seawater is pumped from the coastal lagoon, and then it goes to the tank. And the pH acclimation of 2 weeks, we start like first we left them at the control, and then we start like lowering like 0.1, like every 4 days, depending on how the system was responding. We try to make it as gradual as possible.
Yeah. And did you consider simulating natural variability of pH in the experiment? You said that's rather not possible, right? That's with a pH controller.
Yeah, but this system is very resistant, and you can put like the range. So the range was 1, and you actually have different levels during the day.
Okay.
Or even like the objective is that you have 3 different pH levels during the whole day, and they change the same. Okay. That's what we try. You could improve it, but that's why we all have to work to increase to include the natural variability in ocean acidification experiments.
Yeah. And I'm sorry.
Sorry.
No, go ahead.
Oh, it's the third question.
Yeah. Did you consider acclimation of organisms to natural local temperature?
Yeah, like that's an interesting question. In this case, the organisms were I did not change the temperature, so they have the temperature that they will have under natural conditions, and the experiment lasted 200 days. So there was some seasonality. We have at the beginning we had some mortality, but it was in all treatments. And it was because the experiments started in December, but then when the temperature rise, there were no mortalities, and the organisms were already adapted to the temperature and pH conditions. But we did not change the temperature. They were the natural temperature that you find in the field. But it's important to consider acclimation of organisms to the local conditions, and in this station we have some different conditions, and that's why we did gradual acclimation of 2 weeks.
No, great and interesting, and also interested to read your paper when it's out. So keep us posted. So we move now to our last speakers, and I hope a few of you as well, will stay a little bit longer with us than 11 CET to listen what Marc McCann will tell us, who's a researcher at the Marine Environment Laboratories of the IAEA in Monaco. He holds a PhD in marine environment, and his main scientific expertise is marine radioecology, exotoxicology, and on sustainable aquaculture. And he's in charge of the experimental works at the marine laboratories. So the floor is yours, Marc.
Thank you, Kirsten. Good morning, good evening, everybody. I will be clear and short because I'm the final one. I'm sure it will be more an insight about the future, about the research related to OA. It's not OA by itself, but it will be alkalinity. So let me first share my presentation. Let's do it. All right. Well, the work that I will present is a little bit, as I said, foreseen for the experiment related to ocean acidification. Now we are talking about the solution, and this work will be highlight some of the paper and the experiment that I've been running out last year in collaboration with Sam Dupont and the team that we have here, and we are looking forward also, of course, to collaborate with other people on this topic. So as I presented earlier, we know about CO2 emission, we know about the impact, ocean acidification, and so on. So now the idea with this figure presented by Katyusa a long time ago, it's about acting, mitigate, adapt. And one of the solutions that have been raised and questioned and tested is about ocean alkalinity enhancement. So some of you may know what it is, speed up the natural process, basically. So it's an approach to carbon removal that involves adding alkaline substance to seawater to enhance the ocean natural carbon sinks. And these substances could be very various. Most of the time people are mentioning the use of minerals such as olivine, but also organoids and so on, or minerals that are tested, that I evaluate, or artificial substance such as lime or other byproducts. So the question when you have this solution is, okay, how to optimize deployment, how evaluate the efficiency. But more within the session, what is interesting for us is also to say, okay, is it safe for marine species? Okay, we can maybe improve the role of ocean as buffer for carbon dioxide emission, but the solution, is it a real solution, or is it like another problem that we had in the system? When we talk about adding some substance in marine ecosystem or marine environment, of course, the idea is we increase the alkalinity. So we want to say, okay, is this alkalinity will change? But when you put another substance, there's other byproducts. There's components associated with minerals that we also worried about. In this context, last year, Sam have been invited to this best practice workshop and piloted by colleagues and so on, and organized by the foundation and others. And there was an idea of, okay, what we should consider when we do experimental research on this topic. And we came out with some ideas, and there's more in-depth details and more in-depth chapter about the different approach, the work that have been done, because there's not that much work done, to be honest. And same way that we did it with ocean acidification, we need to come up with some clear approach. In this chapter, and has been shown by Sam, basically we have different options, and in this context, it depends what you want, more realistic, practical, or cost, or more control and understanding what's happening and using more and more replicates. So this is the way that we always look to try to assess the impact of stressors. And in this context, we are focused on the lab experiment. So in our lab experience, as I said, we tested the effect of intervention to artificially increase the ocean pH on marine organisms. Again, we need to learn from the past. A lot of effort, a lot of good work have been done with OA, but there's basically two approaches. We start with mostly the scenario approach. This is very specific, species specific. Sometimes we have the wrong scenario because of what we have in the field is it really not predictive power model, and so on and so on. And then after we go for a phase 2 where we need to understand the mechanistic understanding of the process. So since we start, this has been done at different labs, but in our lab, what we do is we don't focus on the substance itself, but we prefer to go with the change of the totality. And for this context, we use sodium carbonates, and we try to with the main aspect of the biological aspects, and have been used for ocean acidification studies in the past too. So right now we are focused on survival, growth, and calcification using non-nuclear or nuclear application. As you know, IAEA has a lab in Monaco where we train people to do their own research in the labs, and basically here the aspect that we are dealing with is the nuclear approach, so using some retrotracers to try to find out how organisms are impacted by any stressor. And in this context, we use calcium-45 for the calcification aspect, for assessing the influence of change in alkalinity on calcifying organisms. So here are some share of first results of experiments that have been done with Sam and the team here. So first of all, here we focused on larvae from sea urchins. This is a species that we have on the coast here, and we focused first on the growth and on the calcification rate. So basically here on alkalinity, with a gradient of alkalinity going from 1500 to 3500, we can see that there is some impact on low alkalinity on the growth. Same way, you can see for the calcification rate with the same organism that there's a trend going more down. You go in the alkalinity, more less calcification you have in the organism. Similarly, also, we tested the mortality, and in this case, you can see that the optimum, which is 2,500, which is what we consider as control here. If you go up or down into alkalinity scale, you have an impact on the mortality. So clearly, we can see that up and down, definitely on the range, we have something happening with the alkalinity change. And that's recently also with the use of calcium 45. So using to assess the calcification rate on adult coral, we have been seeing that the increase is not significant, and this is really preliminary data. We need to focus on that in the future. We see that there's an effect on the calcification when we increase the alkalinity. So basically, this is the first test. We try to adapt what we know, what the long experience that we have on OA with this new topic. But the reality is that this will be more intense in the future, because what we want also is not only focus on one single stressor, which is in this case we consider as the stressors the alkalinity change, but is also combining the effects. Since, as I mentioned earlier, when you use substance in the real world, when the models and the prediction and the user saying, well, we'll use olivine, we'll use alkaline substance, basically it come up with other compounds and impurities. And that's what we were going to do in the future. We'll change our total alkalic gradient, and then we'll see how, with addition of impurities or compounds like trace metals like nickel, manganese, magnesium, cobalt, and whatever, we'll try to see how this impact the way they accumulate those compounds, which may lead to other problems from a seafood's perspective or for an ecosystem perspective. In the same way, what we want, that's the next step, is also, okay, we have different potential substances that will be used in future. People are already planning economical aspect and so on. What we want to test is, first of all, try to see what is the dissolution process, and other people are already working on that, but in terms of impact. So using this real material to test what is the impact on the organism under lab conditions. Just for some readings, if some people are interested, we just, as I mentioned, there's a chapter that have been published on the topic, but this is a part of a collection led by Jean-Pierre Gattuso and a group of people working on this guide of best practice for ocean alkalinity enhancement research. I think it's in print, but you can already find the different chapter at different topics on the web link that is connected to this page. Kirsten, that's me. If you want to have a question now or later, this is my email, and I'm happy to respond to your question. Thank you.
Thank you very much for this very interesting talk and to finish an interesting session. We have a question directly from Nina. Why did you choose 2,500 macromole per kilogram as a baseline?
Because that's what we have in the field right now. So the species that we collected the organisms from have been acclimated for a while, or have been living for a while in these conditions. So of course, with collaborators that we have in Sweden or in west coast of France, we change our control as this. But the idea is really to cover a wide range of alkalinity. So that's the idea, of course. Yeah.
It was really interesting to see this very clear pattern of the mortality with the baseline. I mean, it's a nice result for some lab experiment. Luia also has a question. Thank you, Mark, for that interesting talk. What would be the best OAE option to implement in the warm Pacific Islands? Also, would the OAE idea and approach be considered as a commercial venture in the future? For example, could this have an income money-generating benefit for governments to consider?
Well, that's a great question, but I cannot answer this. So I'm really into the experimental aspect. So definitely, I think the best option is to see what you have already to see on the field, the option that you have. So from a geoengineering aspect, for sure, there's different options. When we talk about Pacific Islands, I would say that see what you have as material available, but definitely no option there. from my side. Maybe Sam, do you have something to add on this?
I actually go first, and then I give
Good, excellent.
word as well to Sam. I think it's indeed there's now a lot of pressure on countries and on individuals to kind of explore the ocean as a solution for decreasing CO2. I think it's still something as well. Mark mentioned these guidelines will help a lot to, at least for the research, because we are still at the research stage at this point to help countries to evaluate where they are and what can be done in that field and to which extent it's feasible, because getting the alkalinization material is already quite something. So I think we are all looking forward to these guidance to be published, and it's long awaited. And there are some ambition as well to get carbon crediting for that, whether that weighs out the cost. That's also something, again, I think for some geoengineering experts to evaluate and to consider. But yeah, definitely still in a research space. Sam.
Yeah, I was about to go along those lines. So basically, that's a nice idea, but we always have to be careful with ideas that are very intuitive and looks like a good idea on paper. There's a lot of interest from industries and so on because of the carbon crediting. But the thing is that, to be fair, we have no idea how to implement that. We have no idea if it works. We have no idea how to evaluate how much carbon it's going to capture, if any. And there is no idea about side effects. So that's going to be a little bit of an interesting battle between scientists who are trying to gather the first data on how to evaluate and the consequences, and the push of the industry, of many industries that are willing to do anything to not change their current behavior and instead buy their way out. So I think I would be a little bit careful in jumping into trying to make an industry or a business out of it, because at this stage we just have no idea. You muted, Kirsten.
Thank you very much. So one more question as well from Jesse. How does this group think about the challenge of conducting IAEA experiments in the field where no strong baselines are developed? I'll just give it a try as well. I'm concerned. I would say from a scientific perspective, and ocean, somebody who quite likes the ocean, concerned. I think that is very where I'm personally, and also from our agency, looking at it with care. I think there needs to be a proper risk analysis each time these type of experiments are done. There needs to be a proper rigor scientific approach to it, and of course things should be tested, but I think there needs to be, as Mark as well explained, there need to be different stages of science and experimentation, and I think one has to go step by step, because panic is not useful, because there's a lot of panic, which is good, because there was for a long time no action to climate change and whatsoever, but panic is probably resulting in very bad results as well. So we need to have a proper approach to it, going step by step, doing experimental work in the lab, then small scale, if these are successful in the open ocean or coastal areas, to potentially explore and then still look at the cost benefit. I think that's important, because if you need a lot of energy to get the material for CDR, then it might be not worth it. But that's, again, the last one was maybe more personal.
Now, from my side, I will join some lines about the same way. I think that there's a big concern, and it should be a big concern. From my point of view, I'm not part of this group, so I'm just trying to assess in the lab so I can control the things. It's remind me the past with the iron, and I'm sure you know better than everybody about that, Kirsten. But this is really an interesting aspect. Yeah, there's a chemical aspect. They are already working on that, but my concern is more about the deployment on field. I guess from an experimental point of view, there might be more care about that, but then when you go for, as mentioned by Sam, for an industry that are interesting, that's another level again. So I think we need to be step by step, and that's why also the concern was to first of all try to see, okay, what's the side effect on that? If you put it, have a good idea, but the downside effect on that, what's going on? So step by step, I think we need to, and that's why also the baseline, the guide was also put together. I think it's also, don't do something stupid before. Let's find out and let's come up with some strong knowledge before going for this big scale thing.
Maybe if I can add something, is that it's already happening. So it's not like if it's science fiction that they will wait for our opinion to do it. It's already happening. It's been deployed in some places. It had really strong public reaction, so people got expressed concerns. So I think there is also, like, beyond science, there's also probably like a communication about like informing people, and in some places probably use the precautionary principle. But there's a lot of pressure, so it's going to happen that we like it or not. So in a way, maybe that's a way of framing what kind of science we need, like a little bit in the OARS ID, like it's going to happen. So what can we do to make it the best possible and limiting the negative effect? It's all about trade-offs at the end of the day.
Yeah, totally agree. And iron fertilization again is as well happening again. So it's not, or explored again. I think, of course, we have to go step by step, but probably more outspoken as well about some of the concerns, and using platforms like the UNFCCC COP as well to make that statement. And Jesse just put another comment there as well. Perhaps makes sense for more regional OA monitoring investment at bigger scales. Yes, but monitoring won't help us in. Will help us definitely in getting the baselines and in getting some of the local information, and then also showcasing the impacts. But we also need to be, I think, vocal about certain risks. And again, this risk-benefit precautionary approach. But
and something something that has been discussed also in the best practice group is the fact that we have to be careful, because we said, like in the OARS paper, that we need to be more inclusive and work across community. But the risk is that people who want to test that will go into places where the regulations are a little bit less or more flexible, like in developing countries. So we have to keep an eye on that it's not, again, like we're not exploiting developing countries to play the sorcerer apprentice.
Yes, thank you very much. And what a change in the biology session, but it's, I guess, also showing where a lot of interest goes now. So I would like to thank all the speakers, also my co-host, Sam, the GOA-ON Secretariat for really making this possible. I think it's a great opportunity for many of us to hear about ocean acidification science we are not familiar with every day. And so that's from my side, also saying, enjoy the last day of GOA-ON week. Won't happen for the next year. And yes, register your commitment for OARS, learn more about it, scan this QR code, and looking forward to seeing you all soon.
Thank you all for being part of this session, and thank you for organizing this to the moderators. We thank you all in the audience as well for participating and for the very interesting and thought-provoking questions. Always great to see interest in the audience. And please don't hesitate to look at the schedule. We have, as Kirsten said, we're on the final day, but we have 3 more sessions for you today. So please have a look and register if you'd like to follow those. If you'd like to stay up to date with the GOA-ON community, please consider signing up as a member. And you can do that by visiting GOA-ON.org. And as was mentioned, to discover more about ocean acidification research for sustainability, please scan the QR code and consider submitting a commitment. With that, I thank you all very much, and we hope to see you next time. Goodbye.